Okay, Bill Gillespie here. Going to start on a little lab session here. I thought what we would do is, as I think I promised, that we'd go over a bit more about the Bugs model library and how to do user-specified models. So we're going to do that. As you should have gotten email notification of, you should see that the yeah, let me get my brains working here first. Anyway, the midterm exam has been posted. I set it up so that you have up to, I believe it's November 23rd to complete that. And the way I set it up, you'll see, is the questions themselves are actually just in a PDF document, but the answers are done using the course website. There's essentially like an answer sheet that you open up and click in radio buttons to indicate your answers. So when you after you have a chance to look over the questions and pretty much think you know what you want to answer, go ahead and open up that answer sheet then and fill in the answers. Okay, let's go ahead and get started. What I've opened up, as you can see here, is the user manual for BUGSModelLibrary, and just wanted to go through the section here describing the process of putting together your own models, which in turn, when you do this, it will create a function that can be called from within Bugs. And I think what we'll probably cover today, I don't think we'll go through both the general linear and general nonlinear models. We'll probably just do the general linear model today, but I was going to step you through that process. I guess during our last session I closed out sort of showing you some of the elements of the kind of function that you have to edit, but there's a lot of other bits and pieces you have to do to actually implement that function. So I'm actually going to go back and revisit kind of what we were doing last time, but we'll do it in the context of a real problem. Or a real problem. It's a simulated problem, but we're going to use one of the examples that's actually in the BUGSModelLibrary distribution. Let me actually drag you down to the part of the documentation that's relevant to what we're going to talk about. If you look in the documentation, what you'll find is there's a section. Let's see, where does it begin here? It says, yeah, section beginning using the WinBUGS model library, and talks a bit about the model the way the model functions are structured and so on. And of course, we've already done that in the context of the built-in models, but let's see what we can do in terms of some user-specified ones. I'm going to use the examples that are actually described in the document here, and you'll see it describes how they were simulated, and we're going to be using the same models as the ones that were used for simulation in order to fit the data. So it describes this a bit. You'll see it talks in terms of there being 3 different simulated outcomes that were simulated. There are plasma concentrations, and there's 2 different pharmacodynamic measurements that let us illustrate both the user-specified general linear models as well as nonlinear models. So you can kind of exercise all the components of BUGSModelLibrary from this example. The simulated example is a simulated phase 1 study as part of it, as well as a phase 2 trial described below. Where did we go? There we go. In our phase 1 study, we've got it's a parallel dose escalation design, 25 subjects per dose arm. You can see that we've got 4 active doses plus placebo. Of course, the PK data in this case is just the plasma concentrations of the parent drug. And then for pharmacodynamics, we've got 2 outcomes here. One that I just termed response 1 here was generated using an effect compartment model, and where the effect itself is an Emax function of the concentrations in that effect compartment. So you can see in here, now that we've got an effect compartment, and I guess what I didn't actually say, I said plasma concentrations of parent drug, and didn't say what, in this case, they happen to be generated from a 2-compartment model. Sorry, in fact, let me double check. I think it was 2 compartment with first order absorption. Yes, in here. So when we do the effect compartment, we've got a 4th compartment to deal with, because in the 2 compartment model with first order absorption, we've got 3, because we've got our 2 2 compartments describing the body plus 1 for the absorption site. Now we've got a 4th to deal with the effect compartment, and so now we're getting outside the range of what you can do with the built-in models in BUGSModelLibrary, so the user has to write it himself. But at least in terms of the concentrations, the model is still a linear compartmental model, so we can use the general linear model component of BUGSModelLibrary. Then there's a second response in there which results from an indirect effect model where the drug effect is on the exit rate constant K out within that, and it's a nonlinear effect on that K out. So in that case, it's a nonlinear compartmental model that can't be done using the matrix exponential solution approach that the general linear models does, so we have to specify the model in more general terms. So that would exercise our general nonlinear model case. For that study, we've got PK and PD measured at the same times, and you can see there's several sampling times out to 24 hours. And then there's also a phase 2 trial in here, which is fairly sparse samples from just in this case, we're just describing a single treatment arm here where we've got multiple doses over 7 days within that. And I'm trying to remember if I generated both PK and PD for that. I think I did PD for that too, though it doesn't explicitly mention that here. I guess I'll know that when we actually look at the example again. I haven't looked at it in a while. Excuse me. So the model is described down here. And I've kind of described it in what you could think of as being almost like a, well, I've used sort of the statistical literature approach to describing it. Again, that's somewhat similar to the way you would describe it within a BUGS model. So in this case, the concentrations are log normal. I have a log normal residual variation. Then the expected value comes from our 2 compartment model with first order absorption. We've got log normally distributed parameters in there with some body weight adjustments in here. So this is actually very similar to what you did for hands-on example 3, actually, if you were only looking at the plasma concentrations. Let's see, what else have I got in here? Well, this is just pointing out the specific values that were used for doing the simulations in here. And then for our response 1, I've got a normal residual variation on that. Again, we've got a sigmoid Emax model here describing the expected value, and but it's a sigmoid Emax model of the effect compartment, which is why the subscript E here on the concentrations, and that effect compartment is we can see we've described that in terms of a differential equation. So you've got the rate of change in the concentration in the effect compartment is our KEO times the difference between the central compartment or plasma concentration and the effect compartment concentration in here. So when we write out our full differential equation set, we'll have to write it for our 2 compartment model with first order absorption plus this additional differential equation here describing what's going on in the effect compartment. Let's see, and here we've got also some assumptions here regarding the inter-individual variation on the parameters of that part of the model, and you can see the specific parameter values that were used. For the, I guess I won't bother going over this part in detail. We'll talk about the, if we actually get to the second effect here, we can describe that at the time, but I think we'll probably be saving that until our next session. So why don't we skip past that for now. So that's what was used to simulate it, but in addition, we're going to be describing this model, our two-compartment model with first-order absorption plus an effect compartment, we're actually going to be coding that using our BUGS model library. So that's the task sort of that I'm setting forth for today for our example. Let's see, we don't need to look over the details on the simulation stuff there. Let's skip over the stuff describing use of the built-in models. Okay, come on, scroll down. Here we go. Okay, and finally, here we go. Okay, so here I'm coming to the section here describing our general linear compartmental models and how we code those and implement our models. And we're going to do the details by sort of showing you, but I just wanted to point out again that there is a whole procedure here that you see it describing. The first component being that you've got to create a new component Pascal model library component, and it basically tells you, okay, go to a certain place within the black box within the black box file folders in here. There's already a model in there written out for this two compartment with an effect compartment in there, and so to build a new model, the suggestion here is to use that particular document as a template that you'll then edit in order to create any new model that you want to do, and so it's basically telling you to create a copy of that. Go ahead and launch the black box component builder, grab your new model component in there and then edit it, and you can see it's describing through the processes the things you need to edit and which components need to be changed in here. And you know what, I'm not going to step through the rest of this going through the words here. Let's actually do it and go through the steps in that fashion. If you want, you might want to have a copy of this around to walk through the steps yourself as you're working with it, but I think I remember them well enough that I can probably plow through it over here without looking at it at the same time. So in that case, let's go to Windows World here. Okay, so we're in Windows here. What I'm going to do first here is actually show you how you can get the examples yourself if you haven't already, since I didn't distribute them as part of the package originally. Let's actually open up a browser here, and let's go to the website where WBDev is kept. It's actually kept at in Google code in here, so let's the URL here is just WBDev hopefully I spelled it right .googlecode.com. So assuming I didn't misspell anything, that should take us there, and apparently I did. What did I misspell? I called it WBDev, which wasn't going to get me very far. You'll see it actually tried to change the name, which is actually okay because the URL I gave you is actually kind of a synonym for the thing I've got up here now. Okay, there we go. So we got WBDev here that you're looking at. And what I want to grab is under featured downloads, the first item here you'll see is called BUGSModelLibrary.zip. Let's go ahead and download that thing. Okay, hit that and hit here. If I was really being totally diligent, I would also do the checksum and everything, but I'm going to be lazy here and not do that. Okay, so we've got our Bugs Model Library there. Let's go ahead and open the folder that contains it, and I'm actually going to move that. Here, we can close this thing now here. Let me move that zip file over to our C folder here. you can, I guess, depending on what you want to do, move it either there, or if you prefer, you could move it into the into the USB drive where you have all your other stuff for the course. And we can get rid of that now. So I've got my BUGSModelLibrary zip. Let's open that thing up. Let's extract here. Boom. Okay. So that's now created a folder here called BUGSModelLibrary. Let's open that up. If you open it up, you'll see there's a subfolder in here called examples. Let's go ahead and dig in there. Okay, so here what you'll see is a mishmash of things. Part of the package includes a version of the same bugs tools and BeagleSB utilities you've been working with. I'm not sure which generation that is. What's in here might actually be a little bit earlier generation, but we've got those there. There's some data files here, our fxa.data.csv, and another one here. Those actually probably look kind of familiar from some of the examples we've been doing in the course. What I'm going to do here is we've got the example I'm interested in is contained in these two files right here, effect cpt example.r and the same thing .txt. So .r is our R script for driving the whole thing, and the .txt then is the bugs model, is our WinBUGS model that we're going to use. So let's start by looking, I can show you that. Let's open up our black, what I'm going to open up now, instead of WinBUGS, we're going to open up the black box WinBUGS in here. Come on, shrink. There we go. And let me go ahead and grab the our effect compartment example. And this actually isn't going to be anything particularly new to you for the most part here. Let's make it so we can unwrap a few things. So this isn't really the new part. This is fairly familiar stuff. You can see in here how it's got our, our usual things that we did before, where we've got our inter-individual variability and the various PK parameters. For modeling this, I just put inter-individual variability on KEO, but in this case made it independent of the other PK parameters as part of this. And so that's, let's see, what else do we have? Oh, okay, so yeah, there's that. In addition, there's inter-individual variability on EC50, log normal again here. And then finally, the call here to the WBDev function is happening right here. Again, that's pretty much the same as you've seen before in the examples we've done, other than the fact that this is now has a different name, our 2CPT, F compartment model here. So this part is the same, other than the name of the function that we're calling in here. So this, and now what this is going to be doing again is it's going to be calculating essentially the amounts in all these compartments, and in this case it's 4 compartments now, so that's why you see 1 to 4 here on the left hand side for the number of columns in our X-hat matrix. And we are sorry, where was I going with this here? Oh yeah, our dependent variables here are both the log transform concentrations, so it's called log COBS, as well as what was named here FXA for our, I guess the hypothetical endpoint here for our response was factor 10A inhibition. So and recall that had a normal residual variation in here, and that thing is going to be a function of the effect compartment concentration, called CE hat here, and CE hat here then is a function of the amount in compartment 4 divided by actually, what am I dividing it? Oh, that's right, I'm dividing it by the central volume compartment of distribution. Keep in mind again that this concentration in the effect compartment is kind of a hypothetical concentration that is normalized to have the same volume of distribution as the central compartment, or if you prefer, you can think of it, it's normalized so that the steady state concentration in the effect compartment equals the steady state concentration in the central compartment. So that's why you see basically the same thing happening in this line for CE hat as you do here for C hat, except that we've now got X hat for the fourth compartment rather than the second. So those are the kinds of differences we're doing here. Again, you can see how it dealt with the R effect compartment model. And actually, I thought I had used a sigmoid Emacs. I guess not. I'm just using a plain Emacs in this case. Okay, so that's part. Most of it isn't too much new, other than the fact that we've got two dependent variables instead of one. Where things are really different is when we start talking about building this function right here in order to use it. So let's take a look at that. Let's shrink this bit down a bit. Now what we've got to do is let's wander down into the Netherlands of our program files directories here. So I'm now in program files, and I've got more junk here than I know what to do with, but the one I want to go to is this black box WinBUGS. Now in your case, you can do this if you go into program files on your on the USB drive that we sent you. There's a program files directory in there. Of course, there'll be a whole lot fewer things in it, but in particular, there'll be a folder called black box WinBUGS. Go ahead and open that thing up. And you'll see that's got a whole slew of stuff, and the main thing you're going to be interested in, at least initially, is to scroll on down to the subfolder here called P-metrics. So let's open that guy up. So we've got that, and then inside of that, open up the folder called mod, M-O-D. Go ahead and open that up, and you'll find a whole bunch of files in here, all or most of which have the this .odc extension on the folders, and those all contain object code, or I'm sorry, not object, source code for various things that have to do with WBDev. Some of these are built in your list. I'm trying to remember the copy that you have. Yeah, you probably have most of these. There might be a few in here that aren't in yours that I've built for other purposes. Some that you probably don't want to touch, for example, would be PK models, because that's actually where the bulk of the work gets done in WBDev. That's where dealing with dosing regimens and things like that is all taken care of, and that in turn calls specific modules for particular models. Okay, so the one we're interested in is this guy right there, 2CPT EFF CPT model. Okay, let's go ahead and grab that and take a peek at that. Oh boy, let's make those letters a whole lot bigger. Okay, I just hit something I didn't necessarily want to hit. Let's try that. Okay. Let's see, how does 16 point look? Okay, so let's take a look at that. Actually, we could probably even get away with 20 point. Let's go ahead and see if that works. Oh, that's right, I got to select the whole bugger. Okay, let's see if we can deal with that. Let's see and unwrap our the lines here. Okay, so this is the thing that you would need to edit in order to create your own new function. Now for the example we're about to do, this is already written to cover that, but let me give you the components. The first rule of thumb here is that for the most part, the things in black you do not want to change. The things in red are the things that you do want to change. One of the first things that you need to do is, well, first things is, let's say we're making a completely new function here. So let's let's actually just kind of I'll just do this as a save as. I could have done this now or done it by creating a copy of the file outside, but as long as we're in here, let's do a save as, and let's give this some kind of other name here. I don't know, whatever. What was that other name that was here that I don't want to use? Okay, let me just stick a I'll just stick a 2 in here. So it's just 2 CPT effect compartment 2 model. Okay, not terribly imaginative, but we'll do that. And the first thing you need to do is at the beginning and the end of the file, you'll see you've got the name here that is the same or should be the same as the name of the file. And let's see, does it appear only in the 2 places? I think so. Let me double check. Yeah, I believe those are the only, it appears at the top. And if we go all the way to the bottom, okay, whoa, too far, you'll see it appears again. So we're going to want to change that. If all else fails, one of the things I often like to do is actually, because we're going to be doing more changes like this one, because we've got another file to edit too, but let me copy that and let me go to we'll do a find and replace thing here. So we're going to do that, and I'll put the 2 in there, 2, and every place that appears I want to change it, so I say replace all, and it should tell me it's replaced it 2 of them. Actually, I'm surprised. I expected a message there, but okay. Anyway, we did it. So that's made the changes to those. So you need to do that. And then we need to go through and change our function to be whatever we need in here. So the main thing, the main task that you have in the case of the general linear model is to assign to this matrix called K matrix. That's going to be a matrix which is going to be however many compartments you have, it's going to be that number of dimensions squared. Okay, so in our case we have a 4 compartment model, so it's going to be a 4 by 4 matrix in here. By default, you can see up here inside the code, it already initializes all the elements of that matrix to 0. As a result, all you have to worry about when you change this is to assign the appropriate values to any of the elements that should be non-zero. And that's what you see going on down here in this sequence of steps, where you can see all the non-zero elements of our matrix being assigned. So recall that our basic K in our case here is, let's see, I guess I never wrote out that K. I was debating whether to write it. I won't try to write it. It's going to be essentially the rate constant matrix for the 2 compartment model with first order absorption, but with an additional column and an additional row. The additional column for the first 3 rows will be zeros, but in the last column you're going to have a KE0 added to it in the, I guess it would be the second column, and then a minus KEO in the 4th column in that 4th row. So what we end up with is what you see right here. So you can see how it just picks off the elements of the rate constant matrix. And here's a chance, also a reminder here, that Pascal has the quirk that all indices for matrices and vectors begin with 0. So what would be K matrix, or what would be for the original rate constant matrix, the 1, 1 position becomes the 0, 0 position when we write it in component Pascal. So you can see here our K matrix 0, 0 is minus KA. So and then so on down the line. Our K matrix 1, 0 is positive KA. Got our K matrix 1, 1 is going to be minus the exit rate constants for compartment 1, and so on down the line, where we add in our our intercompartmental rate constants. Okay, all of a sudden the computer slowed down. Let's see. Hopefully it won't keep doing that for our K21, K12, and so on. And then again, finally dealing with our effect compartment in here. Now, of course, these names KA, K10, and all that are not, are not predefined. Those are things you define yourself. And in fact, when I told you your task was to assign values to the non-zero elements of the K matrix here, well, I guess what I needed to complete that sentence, because you're going to assign values given that vector theta that you've passed from WinBUGS. So if we go scroll up to the top, you'll see that one of the arguments in this procedure, because what you're actually doing is filling out the components of this procedure. For those of you that think more like Fortran, procedure would be equivalent to a subroutine. Is the first argument here is theta, and theta is going to be the vector of parameters that you've passed from the from WinBUGS. It's going to be the items in it will be in the same order as they are in WinBUGS, but again, you have to remember that inside Pascal, the first element will be the 0th element instead of the first element. And so again, your mission then is to take those thetas and use them to assign appropriate values to the non-zero elements of K matrix. Now what I've done here is, my habit is to try and make this a little more readable by then saying which theta corresponds to which parameter, using names that are in some ways meaningful to those of us that would be reading it. So you can see where and in that way it becomes somewhat self-documenting. So you can see here clearance corresponds to theta 0, Q to theta 1, and so on, down to KEO corresponds to our theta 5, which again in BUGS actually corresponds to theta 6. But then in order to do this in terms of our rate constant matrix, I have to take the original parameterization in terms of clearance and volume, convert that to our rate constants. So that's what all this nonsense is right here. And then finally, I was using the assumption here that for each individual, Ka is greater than, which one did I assume it was? I guess it's greater than lambda z, is the way this happens to be written out. And thus I made K. So the dKa that was used here is actually the difference between Ka and lambda 1. So in order to calculate Ka, I need to calculate lambda. I need to calculate our lambda z actually in here and add that to dKa. So that takes care of that particular constraint. And then finally make the assignments to the K matrix. The other part in here that you'll see is in red are declarations for any variables that you're using. Now some of them are already, the K matrix for instance is already predefined. I've predefined indices I and J in there, but anything else that you create you need to declare. More often than not, those things are going to be real variables here, and so you can see what I've done here. So for all of these various variables I've created down here, I've had to make a declaration. So you'll find that if you don't do that, you will get an error during the compilation. Let's see, is there anything else I need to tell you? Oh yes, there is. The other part that the user needs to deal with, and this is part of what I want to get automated, because this is the kind of thing that could be automated but hasn't been, is you have to add in these things, and let me tell you what they are. This m.n parameter is the number of model parameters, and when you count them up, remember to include the f's and the t-lags in here. And did I get this right? 12. That doesn't even sound right. I'm surprised I got away with that. let's see, how many parameters do we have up here? We have 6 parameters going from clearance to KEO. So that's up there. And I have 4 compartments. That should, I think because it never used them, I was able to get away with it. But actually, I made a mistake there. Because it should be, there should be 4 T-lags and 4 Fs. So a total of 8, and then I have to add those to the number of parameters here, which would be 14. So that should have been 14. Okay. Now where is, and then the next one, this m.f1 index, is the index associated with f1, which would be the first of the f's. And the way I've written this is it would be the parameter immediately following the last one of these. So here I'm going from 0 to 5, so the next index would be 6. So logically that would be the 6th one, which it is. And then let's see, I think I actually got that number right. I'm still amazed that 12 worked without an error, but anyway. So I think 10 is okay for T-lag, which would immediately follow the last of the F's, because the F's would be in positions 6, 7, 8, and 9, and then the T-lags would be 10, 11, 12, 13 in there. And again, this reiterates then the number of compartments as the last item here, this m.n compartment. So the user has to specify all of those elements the way it's set up right now. And that's all the red stuff. And so those are the elements that would need to be changed in order to create any new function. Then, once you think you've gotten it down, then we need, well, first of all, you need to save it. So for any changes, so let's go ahead and save. And then you need to compile it. And compiling it, you get to by going to the menu called DEV, which presumably is short for development. Okay, let's open up that menu. Boy, it is slow. Why? Okay, we go to, and then select compile and unload. And okay, there we go. And if everything worked out fine, you would get an OK here at the bottom. So you can see this tiny little OK right down at the very bottom here. If you have an error, so for example, just to give you a sense of what an error might look like, let's say I forgot to declare KA here and did that. So let's see what happens if I do that. Okay, come on, there we go. Okay, well, a few things happen. First, on the bottom, you'll see it says undeclared identifier, and you'll see it puts a little block up here on where it believes errors have occurred, and so you can see one right here in front of KA. So it's telling me, okay, that's the undeclared identifier is KA. So that's an illustration of the kinds of error message you might get. Let's go back up and fix it here. And save it back again. And compile it. Okay, and it says okay. So we've got something that in theory can be run, but we're not done yet. We've created a function which is located in the right place and everything to use with WinBUGS, but at this point WinBUGS doesn't know the function exists. We have to do something else, and in particular we have to create well, first of all, there was a package that a while back David Lunn created for users to build their own functions and distributions for WinBUGS. He called that package WBDev, and it's WBDev that I'm using in order to construct a wrapper around this WBDev function, around the WBDev functions I've created in order to link them into WinBUGS. So we have to do that. So let's go down then. Where I'm going here is we're going to go down to another folder inside of black box WinBUGS called WBDev right here. Okay, come on, it's being terribly slow here. Okay, why did it? Okay, and I want to go into the mod folder within that. And what you should be looking for then is, again, if you're going to build your own linear compartmental model, let's go ahead and use that 2 CPT EFF CPT model .odc. We're going to use the one that's in here as a template again for that. So notice it has the same name as the thing that we built inside the pmetrics folder. This time let me go ahead and do this as I'll do it like a copy and paste here. So I'll do a copy and then a paste. Okay, where to go? Yeah, you can see it called it copy of. And let's go ahead and rename that. Okay, recall we put a 2 right there. Okay, so we've got that. Let's go ahead and grab that, and we're going to edit that. This job turns out to be the easier one. Okay, again, let's make it big enough for somebody to be able to see it that has normal eyes. Let's see. Okay, let's okay, now this one turns out to be real easy. Again, the only things you want to change are the things in red, but if you look through here, what you'll see is the red things are all going to look pretty much the same. They're just going to be the name of our module here, of our file. So you can see a couple of them up there. If we scroll down a bit, I think it shows up once or twice more down here. Yeah, there's another one there, and I know there's definitely one at the end. So basically we need to change every place that is to the name that we're now using. So let's go ahead and scroll back to the top. So let me do like I did before here. Actually, maybe it's already still in the okay, that's not the one I wanted to do. Let's try that again. Control F. Okay, we've already got it there, so I don't even need to enter it here. We're going to change our 2CPT effect compartment to 2CPT effect compartment 2. We'll say replace all. Okay, so we went ahead and replaced all of those, and we are actually done, other than the fact that, again, we have to compile it. So if you're curious, you can look. There's a bunch of component Pascal code inside here that essentially links the function we wrote inside the pmetrics folder to WinBUGS. But you don't need to change any of that. You just need to change the name. So we need to save it. And then let's go ahead and compile it. And compile and unload, and everything's okay. It says okay. Okay, we now have all the pieces we need to actually to use it now with WinBUGS, don't we? No, we don't. We have one more piece. This again is part of the WBDev stuff. Let's actually shrink that down now. Let's go back in here, and again we're still inside the, come on, we're still inside WBDev here, but inside there's another folder called RSRC. Let's open that guy up. And what we're interested in is this this file called functions.odc. Let's grab that guy. And basically all functions ODC is kind of a lookup table. Again, let's make, oh, okay, we don't need to fool with that too much. What you see here is a list of things here. Notice there's a bunch of names here. They happen to be names of functions that are being defined using WBDev. The one that we're interested in here, I guess, is, you can see right here, this 2CPT effect compartment model here. What we actually want to do is take that line and make a copy and paste it. It can be anywhere, but I'll go ahead and paste it right next to it here. And I need to change the name. So in particular, over here on the right, where it says WBDev 2CPT effect compartment model, I'm going to put the name of the function that file we just created in there. The left-hand side, the names here that are in blue, are the names which you're going to use inside the bugs models themselves. It doesn't have to match the name over here on the right. I think in almost every example here I happen to have written them that way, but you don't have to. If you'd like something shorter, for example, you could make it shorter. But for now, I'm going to go ahead and use the same name. So it's the 2CPT effect compartment 2 model in there, and then you just save that. This one you don't compile. This essentially is just amounts to essentially an ASCII file that says what the relationship is between the particular WBDev function and the name of the function that you want to use inside WinBUGS. And I think I just messed that up. I undo what I just messed up. Okay, come on. Undo moving. There we go. In here. So anyway, it's just a lookup table. The only other bit that is these, where you see all these V's, for example, and in some cases an S, is that just says on the right hand side, it's basically telling bugs how many arguments there are going to be inside the bugs function, and this happens to correspond to all those arguments that we have, where you've got like what was it, I always forget the order, but it's, you know, you've got things like time and amount and compartment and so on, and the last one being theta, and then the returned value itself is also a vector, vector matrix actually. In here, it's thus the V on the left side. If it's an S, it means it's a scalar value. Okay, let's go ahead and save this. Okay, now we've done all the pieces needed to create a new bugs function, a new WinBUGS function by the name that I've highlighted there. So we can now use that if we want. So let's go ahead and do that. What I'll actually do is let's go back up to our examples folder up here. Okay. Okay, what was all that about? There we go. Actually, let's see if... Glad I'm not doing a lot of computation today, because for some reason everything's being very slow. Let's shrink that down a bit, and I can't remember if I kept the model open, did I? Yes, I did. Okay, recall this guy. This was the bugs model we're actually going to use. Let's go ahead and change it. Let's go ahead and change it to the name we just defined. We'll put a 2 there and a 2 there. And in fact, let's go ahead and save it using that name for the model itself too. It doesn't have to match. It's just that I didn't want to overwrite the. Oh, I just did overwrite it. Never mind. Let's go ahead and do it again. Okay, I'll call it effect compartment example 2. Okay, let's save that. Okay, so that's the model we're going to use, and in fact we can go ahead and close our black box WinBUGs here. And let's see, I guess I don't have R open. Let's open up R. Okay, let's open the appropriate R script here. Okay, this was our effect compartment example. Let's go ahead and again save that as under the other name here. Let's see. Oh, come on. It's not smart enough to save it in the same directory. Okay. Okay, let's stick a 2 on that. Okay, and let's see. Okay, so we've got a script similar to the ones that we've been using within the class. There's a few differences here and there. Let's see, our model name here. Let's change that to put a 2 on it here, so it picks off the appropriate model. Let's see if I need to change any things here. Let's see, that's the right directory. Okay, let's see, black box WinBUGs. Yeah, I think we're actually okay there. I think everything's okay. We'll find out soon enough. So other than changing the name there, we don't have to do anything fancy. And otherwise, this is very much like any of the other ones you've been used to using. I don't think there's really much in here that I need to change. So let's go ahead and change clear WD to false in case we want to do anything with the files we get for debugging. Let's actually see if it runs. It takes too long for us to actually finish while we're here, but at least we can see if I made any serious errors we need to fix. Let me go ahead and just run it up to here first. Grab the wrong bit. Okay. So far so good. Okay, it seems to run okay up to that point. Let's see if it's capable of firing up the thing we've got here. Okay. Okay, yeah, found it and everything. Okay, so it'll certainly take a while to actually run that, but at least it seems to have figured out where it is, and so it's actually identified the appropriate function. So we've actually defined it. It's capable of getting to it and actually running a model with it inside of it, so that'll take care of that. What you may find if, okay, that's not good. In case you haven't seen a trap before, there's a trap. And I wonder what I did, because I didn't think I changed anything that would have caused it to... Maybe it didn't. Maybe I did some calculations in my head that weren't right when I said we needed 14. Oh, I know why. Because I said we needed 14, but I never defined 14 appropriately in the model. That's the problem. That's what I get for... That's probably why I was able to get away with it before. We can fix that pretty quick. Let's grab our model function here. So that was our, where is it? Effect compartment example 2. We're going to run out of time pretty soon here, though. Let's see. What it was upset about is right here. Recall that I said, gee, I made a mistake. I should have had one F and one T lag for each compartment and didn't. And I took care of that in the BUGSModelLibrary function, but I forgot to take care of it in here. So what I need to do here is create another F here, and we're going to create another T lag. Then I got to fix up the so that's going to be our F4 here, and I got to fix up our indices. Okay. And we have to do the same thing down here for our posterior predictions. By the way, certainly feel free, if you've got any questions, feel free to ask while I'm doing this little bit of bookkeeping here. Okay, I think that's the pieces here. Let's see. I think that's all I needed to change here. Yeah, okay. Save that. Let's end it and let's try again. And I guess I'll just say that the one good thing about you seeing me make a mistake like that is it maybe helps you figure out how to fix your own as you go along. Okay, it's updating now, so we solved that part of the problem anyway. Okay, so as I say, this will take too long for us to sit here and watch it since we've pretty well run out of time anyway. Let's see, I do have one question here. Let's see, what do we got? Okay. Okay, well, somebody was asking about not understanding the matrix formulation of the model well, and in particular, why do we have some negative rate constants in there? Actually, the rate constant's not negative, but they're elements in the in the matrix that are negative. Trying to think if there's any quick way to sort of write this out. Maybe I think if I can get myself a piece of white real estate I can write on real quick here. Let's see. Well, cheat. We'll do it this way here. That doesn't work so good here. Let's see. Well, maybe I can write it out using it. What I need is a quick whiteboard, but I don't have one handy here. But let me see if I can give you some idea what we're talking about. So let's talk about a very simple model. In particular, let's talk about two-compartment model with just a two-compartment model, no absorption in it. So for that model, you would have, say, like x1 prime, in other words, the derivative with respect to time for our central compartment would be minus the sum of k10 plus k12. I never have figured out how to write very legibly with this. You'll have to excuse that. Okay, that's going to be times x1, your central compartment. Then that's going to be plus the return, which is going to be k21 times x2 from the second compartment, or peripheral compartment. And then x2 prime here is going to be it's going to be k12 times x1 minus k, where are we going here, k21 x2. The matrix formulation of this is to just convert this into a matrix expression involving the vectors x prime, which would be the combination of x1 prime and x2 prime, and then x, which would be the combination of x1 and x2. And I guess I'll use the little white bit on the bottom here to try and write that out. Okay, where did my, there it is. So that would be written out as something like x prime, whoops, and it's supposed to be an equal sign, believe it or not, would be, you know, some capital K here times x in here, and k in here wouldn't be nothing more than what you get from up here. So the 1 element here, let's put the bars on it here, so that's going to be minus k10. Oh boy, my writing is getting worse here on this. I need a bigger tablet here. K12 here, so that's the 1 element. The 1 2 element is going to be a positive k12, or k21, sorry. And then down here we're going to have k12, again it's positive. Oops, and then over here we're going to have minus k21. So again, it's just a matrix expression equivalent to the two equations that we've written up on, that I wrote up on top here. So that's how you can get stuff like that. Let's see here. I think if there was any more goodies down here. Not really here. So that was pretty much the story I planned on telling you today. My suggestion to get a handle on this would be to, you know, identify a model that you might want. In fact, actually one simple, relatively simple exercise would actually be to take a problem, say like hands-on example 3, and redo it, but using a user-specified model, where in that case it was a two-compartment model with first-order absorption, with no constraint on the individual KAs. Go ahead and write that out as a set of differential equations. identify, and figure out what the appropriate rate constant matrix is for that, and implement that using the approach we just described here, and actually attempt running essentially redoing example 3, but using a model that you've written yourself using this functionality. So that'd be one approach there, where you've got the data at hand. And of course, if you've got your own problem, your own data that might be described by a model where it's applicable, go ahead and take a crack at that. I guess in the meantime, we'll take a look and really thought through exactly what we'll do on this coming Monday, but I think part of it will be talking about how you can do a similar sort of thing for nonlinear models. So I guess until then, if there's no more questions, I guess I'm going to go ahead and vanish, and see you on Monday.